Now let me switch and talk about some recent results from niobium thin films. These are just niobium now, using our CED coater. The first message is RRR of more than 300 in a micron thick niobium film. This is very exciting. This could be a major breakthrough for SRF, who knows. I'd just say that we've achieved bulk niobium-like RRRs for the first time. And I'd want to refer you to the very next talk by Anne-Marie, who's going to show you, using ECR, a RRR of 223. Now, these numbers are quite exciting. They're new, and they tell us that thin films might have come of age. So now I'll show you some of the data. What we did was we systematically varied the substrate heating temperature and then the temperature at which we did the coating. So as you can see, it's a dense matrix here. You can heat the thing to 150 and then coat it at 150, or you can heat it to 700 and coat it at 150, or heat it to 500 and coat it at 700, etc. And we just sort of negotiated our way through this matrix. And you can see on A-plane sapphire, the RRR screams up from nothing to 155 here. Now, I'm not saying that we're going to go and coat some SRF cavity at 600 degrees C for obvious reasons. But the point is to see what we can learn from this kind of activity that we can then apply back to the SRF problem. And if we look at niobium on MgO, this is where we got these rather spectacular results, a whole series of RRR measurements that exceeded 300. Now, initially, we were skeptical about using MgO as a substrate because people use A-plane sapphire because of the better lattice match and so on to niobium. And a priori, MgO has a terrible lattice mismatch for BCC niobium, and it's an FCC crystal. But one of the ideas was, could we put MgO on copper and use that as an intermediary between the copper and the niobium? Again, there's been talk about heating the copper and having interdiffusion between copper and niobium and so on. Another practical reason for growing an insulator first and then putting the metal on, apart from the ones that Claire showed us, is that it gives you a very simple way to measure RRR even though you have a metal substrate if you first put an insulator on. So those were the things that motivated this. And the result was a delightful surprise. A very nice RRR result. And we're preparing a publication on this. And the next step, obviously, is can we bias the substrates now? And can I achieve the dream of accomplishing these kinds of properties but at much lower temperatures that may be more practical to apply to a cavity? I think perhaps yes. Now, we also varied all of these substrates, A sapphire, MgO, and borosilicate, which I'll come to in a few minutes. We varied the thickness, and recall Larry explaining to us on Monday that a priori one expects that the RRR should be a strong function of the film thickness. It should be pretty poor right at the surface where you're growing your first few monolayers, full of defects, island growth, fibrous texture, should get better and better. And clearly, what one is interested in is just the last 100 nanometers up at the top, the London depth. And so you know that you're measuring an average when you use these 4-point probes. And so the question is the peak value up there higher? And indeed it is. And I've just developed a simple little model based on exponential growth of RRR, and I just fit it to these data. And we need to do more on this, obviously. But the message is that the actual RRR for MgO for niobium at the top of the film might be more like 400 rather than the average value of 333 that we measured. And in the case of A sapphire and borosilicate, if we made thicker films, they may asymptote up there too. Now, a very, very brief survey of the literature. This is a very dense chart, and I don't expect you to read it. I'll just hit the high notes here. I organize these RRRs in ascending order. And the devices that I've compared with are E-beam evaporations, different vacuum arcs, ECR sources, and so on. Some of the trends that are pretty obvious are the thicker the films, the higher were the RRRs. That's pretty obvious. The other trend is that the higher the substrate temperature, they needed high substrate temperatures, And another trend is energetic condensation tended to give higher RRRs. It would have been a nice story if it weren't for this nasty exception here. This paper, where they used MBE, where obviously the energies are very low, they yet got a RRR of 87. But it may be because they heated the substrate to 900 Celsius. So you see this interesting combination of temperature, film thickness, ion energy. Might there also be a deposition rate effect? It comes back to what I said. We grow a monolayer in about a millisecond. If I normalize to that rate, which is an instantaneous rate of about 5,000 angstroms, 500 nanometers per second, is the instantaneous rate at which this device is laying down material on a film. If you look at all the other experiments, they were 2 to 3 orders of magnitude slower in terms of achieving the same film thickness. Is that significant? I don't know. We need to study that some more. I have only 29 minutes, so I'm going to go ahead here and now switch gears and talk about X-ray diffraction and EBSD data on these films to try and gain some other insights. This is part of the systematic walk before you run approach that JLab and AASC have adopted. So our colleagues at JLab and Professor Gang Seo at NSU produced these Bragg-Brentano spectra, and I'm so glad that Josh gave us all a lecture on Monday, so you're all now quite familiar with what these images are supposed to represent. I can now zip through them and simply show you what's the key here. Look at the low RRR result versus the high RRR result. This is niobium on A-plane sapphire. What does one see? One sees the pole figure showing the 110 with the so-called twin symmetry. See, you see these 2 extra nodes. They aren't just 2, there are actually 4 of them, with the other 2 blended into these 2. And you see they're sort of diffuse in this psi direction, which indicates sort of polycrystalline structure in the film. When you get up to the high temperature and anneal this thing as you're coating it, you find these 4 dots are very tight, central peak, twins are absent. You've gone to a monocrystalline structure. Now, that's an interesting transition, and that's correlated with getting higher RRR. And it's sort of reasonable to suppose that the monocrystalline structure also has fewer defects in it. And fewer defects, longer mean free path, higher RRR. So it's heteroepitaxial single crystal growth that we're claiming here, correlated with the high RRR. Let's look at the same story, but now for the niobium that was grown on MgO. Again, I walk you through a low RRR result at low temperatures, an intermediate RRR of 181, and then one of the best ones we did. Here's something even more interesting happens. Look at what happens. You go from this polycrystalline 110 orientation everywhere. I should also remind you that the field at which these images are taken is 12 by 12 millimeters. We're not looking at some tiny dot on this film. It's a global measurement, unlike EBSD, which is a tiny spot which we then raster back and forth and which looks only on the surface. These are copper K alpha X-rays. They're penetrating this 1 micron film. When you get to this intermediate condition, you obviously see the polycrystalline behavior is becoming more like a monocrystal. You can see that in the sharpness of these Bragg-Brentano spectra peaks and their intensity. Now look what happens when we went up to 700 and 700. This 110 niobium completely switched to 100 niobium. And it's just labeled as 200 here because that's XRD nomenclature. The pole figure can see only the 200 plane. But it's in the same family as 100. What is this transition in this BCC niobium from 110 to 100 as a function of temperature? How is that correlated with higher RRR? Those are all the subjects of another APL that's in preparation by our colleague Gang Seo, who's the expert on these things. Now let me switch and say a few words about EBSD. We're looking at the SEMs with EBSD samples overlaid on them. Let's just look at the high RRR. This is niobium on MgO. If you look at this EBSD, this is on a millimeter scale here. One pure color, it's all 100 everywhere that the instrument can survey. If you go down to that intermediate RRR, which was the case where we had sort of a coexistence of 110 and a little bit of 100, the EBSD confirms that right on the surface. There's the green, which is 110, and the red, which is this 100. And on a finer scale, going from a millimeter down to 100 micron scale, you see that too, and you see those orientations. The EBSD conveniently plots those little cubes. Macroparticles. This has always fascinated us. We saw this last year when we did this on copper, is that the crystal structure on the macroparticle is identical to that elsewhere. The other thing to note is that this macroparticle, even though it's on this long scale here, 35 microns, so it's 100 microns long, it's not very thick out of the plane. So is that necessarily a problem for a cavity? I'm not convinced yet. When one looks at the field enhancements of little bumps like this, they're not as severe as one might think. This isn't equivalent to a columnar whisker coming out from the film, which would truly have very, very high field enhancements. So the jury is out, I think, on whether macros are necessarily a bad thing. And there's a fascinating physics reason why we think the macroparticles are picking up the exact same highly ordered crystalline structure as the ions, which are energetic, are able to drive. And that's because one of the subtle things about cathodic arcs is that the melting temperature actually is elevated because of the very high local pressure at the spot. So you may have a semi-liquid, semi-solid little particle that's coming off, carrying a high temperature in it. It lands on the surface. It might possibly just locally melt the very surface of the niobium film that it lands on. And then it refuses and obviously then becomes a very ordered crystal and acquires the information that it just picked up from the little piece that it melted. And that might be the reason why it's not a surprise that the order doesn't suddenly go to hell because we have macroparticles. Having said all of that, if it really becomes a problem downstream, the engineer's solution is we have that filter and we can filter them out.